model, I should say, when you use model to fit the data, you just remove the ith data point. Then you get a regression line, right? And using that regression model to calculate the predicted value for all the data points, k is 1 to n. The first one is have the full data set with no one deleted. Then you look at the difference between these two, square them, and the sum. Okay, so people still have trouble understanding the ith deleted. This is your matrix X. It is n by p plus 1. That is X. Okay, if the ith deleted basically means if this is ith data point, I will just remove this row. Remove this row from the data set, then use the model to fit this data. You will get a different regression line, right? You'll get a different regression line, then use that regression line to predict yk hat for all the k equal to 1 to n. That's how you get the second one. The first one is the same old, we have seen that before. Okay? All right. So the second method is called the diff fits, the difference in fits. Okay? So defined as diff fits of the ith data point equal to just y hat minus y hat of the, again with ith deleted. It comes from a different model. Then you have a sigma hat with ith deleted and the square root of h I. Okay. So this basically directly measures the difference between the ith with the full data and ith predicted value with ith deleted. Then this is the sigma hat with ith deleted. It can be shown that this diff fits actually diff fits I equal to Ri star, as we defined earlier, square root of Hii over minus Hii. So basically, it has two things multiplied together. Ri star measures what? The degree of outlineness, right? If the data is outlined, it has very large Ri star. Hii here, as we talked about in the property of Hii, it measures how extreme it is from the center of data, from xi minus x bar. So it has two things multiplied together. So together, it basically considers both the outlineness in y and also outlineness in x. If the product is large, this data point is influential. That's the intuition, okay? So if the diff fits sub I, the absolute value is greater than 2 times square root of p plus 1 over n minus p minus 1. We call it influential. Okay? Call it influential.
Is everything under the square root there, or is it just the numerator?
Say it again.
Is everything under this? Is everything under the square root there, or is it just the numerator?
Oh, both.
Okay, thank you.
Yeah. So you notice that what is p plus 1, what is n minus p minus 1? That is the degree freedom in F, p plus 1 and minus p minus 1. Okay. So basically, when we use diff fits as a measure, we already considered both the size of the data set and also the dimension of the data set. Okay. So we basically, by examining the diff fits, we know that the product of the two, one measures extremeness of in y, the other one is extremeness in x. How about the CI? Did you see anything similar? Only p plus 1. P plus 1 is a dimension. It doesn't have a specific value in there. Well, let me give you a hint here. Let me give you a hint. So look at the one I gave you today. There's a reason why I give you this. This is beta hat minus beta hat I. Beta is your regression line coefficient, right? What is y hat and what is y hat I? It comes from x beta. X beta hat will give you y hat. X beta hat I will give you y hat I. What is in there? What is in there? You have EI and 1 minus HII. What does EI measure? Extremeness in Y. What does HI measure? HI measures how far it is it from X bar, right? Xi minus X bar. But HI has minus here. It's also at the denominator. So 1 minus HI together shows how extreme it is in X, right? So basically, in the formula, although you only see y hat minus y hat I, you actually see this beta hat minus beta hat I, which include both extremeness in y and also extremeness in x. Okay, and also in a manner that is multiplied together. All right. So basically, so far we defined two measures: Cook's distance and the dip phase. Both have considered both the outlierness in y and also outlierness in x, and they are multiplied together. All right. The third one. Third one is called Hardy's measure. Hardy's. So HI Hardy's. This is not a hat matrix, but coming from the person's name. Hardy's measure is equal to HII over 1 minus HII plus, this is plus, the previous two measures have multiplied, but this is plus, P plus 1, 1 minus HII, multiplied by DI squared over 1 minus DI squared. But keep in mind, this DI is different from the DI defined earlier. I would like to add some like tilde here to make it different from the previous DI, because the previous DI, as we defined earlier, is the difference between y and y hat deleted. But this DI, the book continue to use DI, which is pretty annoying. I will add a tilde to indicate it's a different thing. This DI actually equal to EI over square root of SIE. Okay, it's a different quantity. Just happen to use the same notation. This is called the normalized residue. Okay, so not the same as DI equal to YI minus Y hat with I deleted, defined before, okay? So what does Hardy's measure here? What does this measure? As I said, in the earlier two measures, you have multiplication, but this one has addition. That's first part, second part. What does the first part measure? The first term, HII over 1 minus HII. It is called a potential function. The second term, P plus 1 over 1 minus HII, multiplied by di squared over 1 minus di squared. And again, I'll put tilde here to indicate it's different. This is called the residual function. The two terms here is called potential plus residue. So what does the potential function measure? What does the potential function measure? You have HI here, 1 minus HI. Leverage, yes. So how extreme it is in X, or the outlierness in X, measures if it is extreme in X. How does residual function measure? Of course, it's also multiplied by 1 minus HI. So basically, you can consider this is the weight of the second part. But what is the di squared measure? Di is defined here, ei is residue. Residue is y minus y hat. So this one actually measures how extreme it is in y, multiplied by something that give the weight. So high leverage point also have higher weight. So together you have both extremeness or outlierness in x, outlierness in y considered, but it's plus, it's addition here. Okay, so all these measures, if it is large, it gives you basically it tells you the data point both have a high leverage and also outlierness. So in the book, it didn't give you the threshold cutoff value for hard disk. Basically, you are looking at, where do I find a cutoff value? So for this part, let's say we don't use the cutoff value. Let's just look at the plot. The first term offered versus the second term. The first term is potential. The second term is residue. Residual function, not the EI, okay? Just the first term versus the second term to plot here. The extreme ones, basically it needs to be like away from others. So this is what we see in the next section. Actually, this is in section 10 here. We call that potential the potential versus residual plot. Keep in mind, this is not the residual versus phase or residual versus predictor plot we talked about at the beginning. That one residual refers to EI, but here it refers to the residual function. And the Y is potential function coming from here, coming from what we defined here. Okay. So in this case, if you see anyone that has very basically isolated and far away from the rest of the cluster, it can be considered as a highly influential point. So I'll show you a picture here. I'll show you. Okay, this one. So this is the New York River data. The data actually included in the book. On the left, you see Y versus X4. X4 is one of the predictor. We don't care about others. It's your scatter plot and also have a regression line here. Y versus X4. And can you, from here, can you tell which point it has high leverage and which one is outlier? Which one is highly influential? If you just look at the plot on the left, it's not obvious, right? You have a cluster of data centered at the beginning around 0 point. And then you have 4, 5, starting from 3, 4, 5, 6, 7, 8. All these data points looks very suspicious, but we don't know in what way exactly it is suspicious, right? Then you look at the plot on the right. This is potential versus residual point. Potential measures how extreme is it in X. The residual measures how extreme it is in Y. So from here, what can you tell? What is conclusion you can draw by looking at the plot on the right? 0.5, is this a high leverage point or outlier? 0.5, what is exactly wrong with 0.5? 0.5 is high leverage, okay? High leverage point, but it's not outlying. As you can see from the plot on the left, it actually is very close to the regression line. So 0.5 is just high leverage, but not outlying. It's just a high leverage point. What about 0.3, 4, 7, 8? You look at from here, 3, 7, 4, 8. What's wrong with these 4 points here? Are they high leverage? They are not high leverage because their potential is not high. Are they outlying? Are they outlying? They are, yeah, they are outlying, okay? So the conclusion we can draw from the plot on the right is 0.5 is a high leverage point. 0.3748, these are the outliers, okay? No one is considered highly influential because if you look at the plot on the left, did 0.5 draw the regression line toward itself? I don't think so because there's 0.4 that actually is doing this. So basically you have 0.5 is just high leverage, but not outline in Y. But 3, 7, 4, 8, they are outlining in Y, but they don't have high leverage, which can be verified from on the plot on the right. Basically, they don't have high potential. And also from the plot on the left, you can see the 3, 7, 4, 8. This kind of point here, they are not extreme in X. 4 and 7 pretty much is at the center, especially 7, probably pretty much at the center of the data. So they are not they're also in the scope of the minimum to maximum X. So are covered in the range. They are not considered outlying in X. So they are not a high leverage. So this is the case where you see the data points are only extreme in one dimension, but not both, and not considered influential point. I see many questions. Yeah, that's the next question. So do we want to get rid of outliers? The last thing you want to do is just delete a data point, okay, which is topic of the next section. We will have some other measures and other transformation. The last thing you want to resort to is just simply remove a data point, all right? But today, let's just, we still have a few slides to go from the previous, we haven't showed it yet, and after this, we'll finish. So this is the slides I posted to Blackboard just today. So this is, on the left, you will see just scatter plot. There is a blue point and a red point. What is exactly the category of the red point? Is this high leverage? Is this influential? The answer is no and no, because it is close to X bar. It's not high leverage and also not influential. Now you look at the regression line on the right. The solid line is with the full data set. The dashed line is with the ice deleted, okay, without the red line. Now you can see the two regression lines are actually very close to each other. Visually, they are very close to each other. And also, if you look at the coefficient, the actual number 2.96, 1.73, that's the intercept. 5.04, 5.112, the slopes are very close. So this point is not influential at all. It is the outlier in Y, but not high leverage. That's why it's not influential. It doesn't change the regression line much, okay? The next one. You see a red point here at the corner and the rest of the blue point here. This point has high leverage, but it's not an outlier. As you can see here, if you put a regression line here, this point, this red point, actually is very close to the regression line. And on the right, you see the solid line and then the dashed line. The solid line is with the full data set. The dashed line is with the ice deleted. As you can see, it doesn't change the regression line much, okay? The coefficient for the slope also doesn't change much. So again, this is a high leverage point, very extreme in X, but not influential because it's not extreme in Y. Then you see this line. You see the red point here. Does it have high leverage? Yes. Very extreme in X. Is it influential? Yes. So for the data point that is extreme in both X and Y, it is influential. As you can see, the solid line is the fitted line with all the data points. The dashed line is the fitted line with ice deleted, with this red point deleted. You can see the slope changed a lot. Obviously, this data point pull the regression line toward itself. So in this case, if you look at every data point, Y hat versus Y hat with the ice deleted, the difference will be large. So this is the influential point. It's both high leverage and also extreme in Y, extreme in Y minus Y hat. So this is a influential point, okay? All right, I think today we will stop here and we will spend maybe like a first half of lecture next time to talk about how do we deal with the outliers. Question? In the graph residual potential, in the potential versus residual you offer, okay, in this potential versus residual. Here, there's no point that is influential, okay? We talk about 0.5 is high leverage, 0.3748, these are outliers. They are extreme in one, either X or Y, but not both, all right? Okay. So next, in that plot, there's no influential point, okay? So I'm going to ask a question.